Recording ball. All right, what questions do we have at the moment? Lots to absorb. Several questions I assume have come up. We haven't asked in Discord yet.
I have a question.
Yep.
I have a hard time to understand big O notation. Can we go over like the practice test and just explain some of the examples, please?
Yeah, we can definitely do that. We'll probably save that part till later tonight. Yeah, big O notation. If I want to talk about that some more, it's.
And also, there is you give me a comment with the order with my array queue that it's not in the same order, and I didn't understand like what's wrong with it.
All right, we can get your code later tonight and check that out during the lab section. See if I can bring up what I was talking about. All right, so back to Big O. Big O is an approximation for the rate of growth for an algorithm, right? So like linear search being one of our algorithms we talked about. If I have a data set of 1 million people, I'm trying to find a random person in this unordered data set. It's going to take so much work to find the person. If I have to do the same algorithm for a data set that's got 1 billion people in it, and then we expect the average amount of work to find or figure out that a person is not in the data set is going to be much larger. In the relative difference in the work between 1 million to 1 billion should be on a straight scale. It's going to be 1,000 times larger data sets. So it's going to be 1,000 times more work on average. One of the other things about big O notation is we're doing worst case analysis. So what is our worst case scenario? That's going to bring us that situation. So for like a linear search, trying to find something that's not in the data set. So when we have a particular problem, such as finding a single piece of data in a data set, we want to see, are there alternative algorithms that can help us solve the problem? And that's what brought us to our binary search. And so let's do our searches. There's the top level. Okay. All right, so linear search. All right, we go then. No notation, our worst case scenario. The last element is the match or the data does not exist in the set. As the amount of work doubles, or excuse me, as the amount of data doubles, work also doubles. And so then we've got our binary search. We have our big O of log n. All right, worst case scenario. And being similar, the big O one's constant time. I'll get to that in a second. The data is not in the solution set. Excuse me, but as the amount of data doubles, the amount of work only goes up by an incremental amount. All right, so wherever possible, we would prefer to use a binary search or linear search. The amount of work to find a solution
And that's because
is
the binary cuts it in half, right, Professor? Versus
right.
a linear?
Correct.
Ah, okay.
Right. It's generally going to be faster. Right. It's generally going to be faster. Right. Both have the same best case scenario where the first element we look at matches the key that we're searching for. Right. That's got a 1/n possibility. Possibility. So, you know, there's 10 items. You got a 10% chance of being successful in the first test. There is 1,000. Right. And another 0.1% chance probability of being on the first success. Right? And on average, all right. So on average, linear is n divided by 2, which is still just big O of n. Whereas on average, binary search is going to be log n still. Right, so linear search, there's a 50% probability that the answer is in the first half of the set and 50% probability the answer is in the second half of the set. So on average, if you were to search for every value in it, you're going to have to go through half the elements to find what you're looking for. All right, so only good reason why we wouldn't always use binary is if we can't justify the cost of sorting, right? And sorting tends towards the go of n squared, as we will see before too long. Sorry, 1 second. All right, so if we're getting into practical situations, so if we plan on searching the data frequently, right, enough to offset one-time sort, then we'll go with that upfront cost to get better return, right? So it's like getting a all at one. It's kind of like the lottery. You want all up front, or you want to get guaranteed higher returns over life. It just all depends on how the math lines up. Sometimes the math favors one way, sometimes the math favors the other. It just depends on what's going on. All right, so our big O complexity cases here, right? So big O1 is constant time. So that means the amount of data doubles, but the amount of work doesn't more or less go up, or at least not in an appreciable way. There might be a little bit of overhead change just because of system limitations, but from 10 to 100 to 1,000 to 10,000 to 100,000, basically going to see the response generated in roughly the same number of operations, which translates to the same amount of time. Logins are next step up from there, where we go, you know, doubling, only going up by 1. Yes?
Right. So what does it mean that it says that like array and it's like O of 1 for the access, but for the search it's O, and what does this mean?
Right, so.
And we have two difference in average and in word.
Yeah, so, right, so average would be the first 4 columns here. So worst case would be big O notation, so I see everything's an O over here. Right, arrays have random access. It takes the same amount of time to get to the first element as it does the last element or any other element, because it's just mathematical calculation. And it doesn't matter if the array is 100 elements or 10,000 elements. It's still just a mathematical calculation to get from the base address to any other address. Right, multiplication addition, we'll actually get into that math later. But, right, searching an array which we can't presume to be ordered, so it has a potential to be unordered, which means it's going to be linear time. Insertion here, I'm not entirely sure what the context of printing here. We might want to bring up Wikipedia here and see what they're saying. But if we want to insert into an array, and if it's being maintained on a sorted basis, then insertion in a sorted array gives here. But we'll talk about the second. Ordered. Maintaining ordered structures is something we will be taking a look at.
What does
Right.
DQ01 mean?
Sorry, what does what of one mean?
DQ of 01.
DQ. Where do you see DQ?
Like, I'm just like, it's not about like, it's just a general question. Like DQ, if it was like DQ needs to be like 01.
Yeah, so right. So DQ, so on a queue, which is deleting from a queue, right? That's a constant time operation. So you wouldn't see any loops, for example, in a DQ operation. You wouldn't see any loops in an NQ operation, just like stacks and queues. So push and pop are both constant time operations, and NQ and DQ are both constant time operations per the definition of the data structure. Right, so if you implement it in such a way that it is not big O of 1, then the implementation is not correct.
So like how we know that we implement and it's a big O one, and how we gonna make sure that it is?
That's where you do the functional notation. All right, so let's do a for example. No. All right, in front. And see, let's do, so we'll do a poor poor implementation to start. Let me see, I want to make sure that the queue. All right, baseline, make sure it's setting to 0. All right, no, too many curly braces here. It's not going to help. Following errors, class Q has, no, I'm missing it. And let's try that again. Someone's already recording. Line 21, I forgot my semicolon. Okay. Always fun switching back between languages. Okay, so our default constructors initialize everyone. I just want to double check there. So bad implementation. I equals 0, I less than count for NQ, for example. All right, if and make that less than equals to I is equal to count. Go ahead and put into our array, which I should create. All right, data sub count equals dat. All right, so we're going a roundabout way to get to the correct position before we insert things. And we drop it in there, and then we increment the count sort of thing, right? So we have a linear solution to a nonlinear problem, right? Where all we had to do was get to the count sort of thing. But I guess this changes. Let's make this actually make sense. front, right? Because if the front goes up and then the count, so this will, right, quote unquote, take us to the right place where we could have just done it mathematically or have a second variable keep track of that for us, right? So what's the functional notation of this method or function? Right, so when we're doing the functional notation of a function, we're going to ignore the actual function overhead. We'll go ahead and just get to the body. So once we get to the body of the function, we have I equals front, right? So that's one operation. I less than equal to count, right? There's the other operator, and then I plus plus. Right, so the count is 0, right? This happens one time. We come in here, we set the value, and then we're done. So void. Still helps to have some data points. Let's equal to count, I plus plus. Data of I, and comma seems good enough. All right, so we go ahead and enqueue something. And we call our dump function to dump it out to the screen. Too many zeros. All right, so our front, and it's going a little bit too far, but whatever. A dump function, we should expect it to be linear because it wants to dump out all of the elements of the array. So whenever you're dealing with something that wants to work with all the elements of a data set, a linear notation is going to be expected, right? Because we have a loop. And generally speaking, whenever you see a loop, the starting point that you're going to be coming from is that it is a linear construct. The key that drives this being linear or not depends on how we're shifting I around. Is I going up by a fixed amount? Is I going up by a fractional amount, right? If we're like doubling I or tripling I, or I is going by scales of 10, then we're not going to have a linear rate of growth because we're not going 1, 2, 3, 4, 5. We're going like 1, 2, 4, 8, 16 around a doubling pattern. The number of iterations doesn't change by much as count increases. Right, so just like we were doing last week, get from here the functional notation of this method by looking at how many times operators are being hit. And then from that functional notation, we can get the O notation. And most of the time, we're looking at loop or nested loops for most algorithms. Occasionally, we'll have a 3-layer loop. We get
So what
down.
was the old notation for this one?
This one is linear because it has a loop. As the amount of data increases, it's going to take longer and longer for the loop to complete. All right, so let me move
So
this
is that line
out.
of code like the O notation?
Well, the algorithm drives what the O notation is. Okay, so let's put a driver in front of this. Go ahead and enqueue a value, then dump out the list. And 1QI. Okay, right, so initially it took us 1 iteration, then 2, right? As the size of the queue grew, the amount of work to get the insert done also grew with it. If this was a constant time, in-queuing operation. It'll be something like this. All right, so see out. Work done. I don't need variables at this point because there's just the one. Right, there's just a single line of code. That line of code is hit one time every time we call this function. Whereas the other one has a looping construct in it. All right, so when you're checking out,
So sorry. So the void function for enqueue, it's a linear. It's not a O, a big O. Yeah.
big O of n is a linear O notation.
So is it a big O?
Yeah, every algorithm has a big O. So let me give you the list. All right, so from the best growth rate to the worst, you go one, just constant time, right? No growth. As the data size increases, all right, log n, logarithmic, rhythmic growth. As the data size doubles, work goes up by a fixed amount. Big O of n, linear time, work doubles as data doubles. If I can type doubles. Then we have linear log. Linear log, right? So that's the composition. So big O of n and big O of log n. We have n times n squared, which is quadratic. Growth rate. And then just further compositions of the above, right? You could have cubic or quadratic log sort of thing. And it's just polynomials. Polynomials. So when we have multiple algorithms that solve the same problem, if we were trying to decide which algorithm is best suited for our snow, big O notation is a measuring stick. Right? We can use complexity classes, compare different algorithms for the same problem, such as searching, sorting, etc. See which is the more appropriate algorithm to use for the solution. Yes, that's the driver. This is why we're talking about big O. And there isn't always a one size fit all. There isn't necessarily the one best sort algorithm. The quick sort tends to be the one that libraries have implemented in them, but quick sort doesn't solve all problems. And there are a lot of ways to sort data. Every which way you can cook an egg, there's there's a sort algorithm, sort of equivalent type thing, right? The problem is cook an egg, and the way to get the egg cooked, there's a whole slew of ways to get a cooked egg. And the results do vary a little bit in the various ways of cooking eggs, but the end result is you have a cooked egg. And that's the high level that we're working on here. Okay. No, the practice test wouldn't expire. It's just it has a date on it to get it in order on the syllabus. Otherwise, if you don't put a date on it, everything just falls to the bottom of the syllabus and makes things harder to find. So that's one of the reasons things have dates on them. Right? Even things that aren't turned in still have a date on it, so that way it stays up in context. All right. Let's see. Okay. No, it's a practice test. It has no point value, it has no bearing on the math at all. Okay, let's see. I think I was going into sorted. You have a queue of nodes. How is it possible for a binary search? Can't, if you have a linked structure, does not support binary search. Binary search, no, well, that's not true. A linear linked structure does not support binary search. We will talk about binary search trees, which are a doubly linked data structure, and that will support the ability to go in the middle because the root is ideally the middle. But that's several weeks away, and we'll talk about that one. Yes, the binary search algorithm applies to arrays as its own class of algorithm. The algorithm for doing a search on a binary search tree is going to be different. Okay, all right, arrays, stacks, queues. So let's talk about ordered structures, which stacks and queues are ordered structures, which you will want to differentiate between sorted structures. Right, so an ordered structure is one, basically we say there is an order in the data. And that order may not be the data or within the say be within the data itself, but rather metadata. All right, so stack is ordered on the first in, last out pattern. Queue is ordered on the first in, first out pattern, right? So it doesn't matter if you're 1 or 100, all data points are considered to be equivalent within these ordering mechanisms. Order could also be based on the data itself, where that order is typically a sorted order. And by default, we will assume ascending order. All right, so maintaining a sorted data set is the problem. So what solutions are available to us? We can maintain a sorted array. All right, as a new data point is added to the set, go ahead and shift all data points that are larger than the new value to the right to make space. And so let's do an example. So we already have a few data points to start, and we want to go ahead and add, right, 7 to the above. First step is we need to make space. And it's the easiest way. There we go. All right, we make space. Step 1, shift all values greater than 7 to the right. And then step 2, insert the value. And we drop 7 in there, and then we're done. Worst case scenario is the newest value is the smallest value. So every value already in the set is shifted, right? Giving us, we go n, right? It's a linear solution to maintain a sorted array of data where data keeps coming into the data set. All right, so that's our first one, sorted array. Our alternative is going to be our sorted.
Question.
Yes.
So basically for the example, the way that we create in space is with like shifting of a number greater than 7 to the right.
Mm-hmm.
And this space is created. And
Yes.
then we put 7. Oh, okay. Got it. Thank you.
Okay, so we can also use a sorted linked list to maintain the data. As a new data point is added, we'll iterate through the list, find the spot, and then update the links and insert a new node. All right, so we'll go ahead and create a sorted list, starting point. When we're drawing lists, we'll abstract some of the details of the data part versus the pointer part. Each of these is nodes in the list. We would have a named node, such as head, or for example, just a pointer, and it would track the first node in the list. So if we have data points like we had before, whatever, 5, 24, 39, and 52. And we want to go ahead and insert 7. What we will do, let's make this smaller, okay. So we create a node, the value 7. All right, step 1, create the node. Because regardless of where we're putting in the list, we need to create the node. So it gives us our node. Next step is Start linking things in there. Step 2. Find where to insert. And this is going to be an iterative problem. 7 needs to go in this list somewhere. And with a linked based structure, we just have head to get us started. So head sees 5. And we'll need to go ahead and find where we're going. In fact, let's go ahead and change this to be 27. Just so we can see the looping part. So what we're going to do is find the node that's going to be to the left. So we found before, which will be to the left of 27, as 39 is greater than 27. So this is where we want to do our insertion. So what we're going to do is now link step 3, link 27 to 39, and link 24 to 27. So we had 27 here, set its next pointer to point to the same node that 24 is already pointing to. Right, so it could be wherever we call this temp node. What do we call this? Temporary previous node, previous next. We'll set both of the pointers equal to 39. And then we can go ahead and let me move this above, get our white space. Oh, better. Okay, so then 24 forgets about 39 and now points to 27. And we have our updated list state.
Hey, Professor.
Mm-hmm.
The algorithm would have to find 39 first, right? The larger number before, like proceeding with putting 27 in between them.
Yeah, we got to find the spot. And that finding where I said iterate, right? That means we're going to have to loop. We have to loop to that position, which means we also have.
No, I was just a little confused because it's previous step said found 24, and then we're gonna link it to 27. Shouldn't it find 39 first? Because that's the greater number.
Yeah, well, we're going to stop when we get to 39, but the temporary node is going to stop at 24 because once we move our temporary node past, we won't be able to alter its state.
Okay, gotcha.
Yeah. So we're going to look at this node. We're going to see, is there a node after it? And if there is, what's the value? And if this value is less than that value, then we stop. All right, so when we started, compared 27 to 5. Okay, we see that 27 goes after 5. So then we go ahead and see, okay, does 5 have a node after it? It does. It's 24. Is 24 less than 27? It's not. So we're going to go ahead and go down the list one spot and make the same comparison again, see if there's a node after 24. And if there is, okay, we'll check its value and then see if 27 is less than 39. It is. We'll stop right there. If it wasn't, say it was 44, we would have gone down 39, test again, then we would have stopped and then set 39's links after 44 was connected to 52, just like we did here. In the other scenarios, if we have to go all the way in, we're adding 60, right? Not less than 5, it's not less than the next one, not less than the next one, not less than the next one. There is no next one anymore to compare against. So, okay, we're at the end of the list and we'll just attach it to the end of the list. Yeah, so step 2 is the loop. All right, so we'll bring the code up from Canvas later to show sorted insert. There's going to be a loop moving our temporary pointers along until we've found the left side of the bridge that we're going to build between or among the new data point and the two existing data points that we're squeezing it in between. And so because of step 2 of step 2, where we have to iterate, and we may well loop to the end, we have a big O N algorithm solution here. So both algorithms or both underlying data structures for a problem of maintaining an ordered list have the same complexity for inserting. Deleting is going to be same problem. We'll need to collapse the list if array based to keep things tight. And for the list, we still need, let's add linked. Linked list, we still need to find position. So still linear. Big O1, which is probably what it was talking about here for insertion and deletion. All right, you can check out the Wikipedia article to see where they're pulling that data point from. But the worst case scenario for inserting would be on an ordered list, in which case we have linear problems because we might have to do a lot of maintenance on the list itself to actually apply the operation. Right, so it depends on what we're going to do next, right? So if our objective of maintaining the ordered list is to search the data based on the information we have right now, then the array based will be best suited for that. And it does have the drawback being an array, which means it's fixed sized. So we'll need additional code logic to resize if needed. Whereas the list, the linked list, didn't have that problem. All right, so if we have a different objective, such as maintaining a priority queue, which may go to Wikipedia. By the way, Wikipedia, this is probably the only programming class I would say Wikipedia is a good website. For data structures. This one, Geeks for Geeks. Geeks for Geeks. There's also a good website. All right, so this community maintained sort of websites. They are pretty good for data structures. And my other favorite website as a professional developer, Stack Overflow. So this one, not exactly the greatest portal for a student trying to learn things, but as a developer trying to solve a problem, It's very rare that you're the first person that needs to solve a given problem. Usually other people have had to solve the problem or run into the same problem. Stack Overflow, also a community-driven website, question and answer forum. When I come here, if I search for something in Google, Stack Overflow is my top 3. I come check, say, okay, does this look like my problem? It's close enough. All right, let me look at the answer. Aha, that's the breadcrumb I needed to figure out whatever it is I happen to be digging into. Apparently, this was one of the more recent ones, I guess. I don't know what my history is trying to say about my Stack Overflow, but good website. So priority queue, right? Like we're talking about stacks and queues, abstract data type or data structure, which says these are the rules that we need to implement, the expected time complexities for those rules, and feel free to go ahead and implement however you want, as long as you're adhering to the rules of the structure. All right, so if we want to maintain priority queue, which is a queue like we've discussed with a basic nature of first in, first out, with the added layer of cutting the line. Right? So it's in your corporate office, you got a meeting room reserved, and then the CEO comes in and says, I need your room, right? See, so certain people have higher priority than other people in a given organization or whatever, or different things, different jobs in the computer system. So telling the CEO to go wait in line is typically not something a junior developer is going to be heard saying, for example. Usually it's like, whoa, and then, you know, very meekly leave the room. So, and here we have priority queue, right? So new data points will, right, insert themselves based upon their priority. So higher priority items going ahead of lower priority and identical priorities following the regular FIFO within that subset. And so, for example, let's do a insert. Let's say we have a priority 2s, priority 4, 5, a couple of 6s in our set. Okay, so here's our priority queue right now. Go ahead and add 3, right? Pretty easy to see where they go in the queue. They're going to cause all these values to shift over, and they'll go ahead of our priority 4 item. All right, if we want to go ahead and add 4, well, I should say 4 dot to differentiate. We already have a 4 in the list. So this 4 dot is going to go after that 4, right? So it's a FIFO within equivalent data points. If I were to add a 2, they come after these 2s. And if I add a 3, it comes after this 3. Anything that's matching goes after those that are priority, because that falls back to the basic queuing mechanism of first in, first out. Right, so if this is what we're looking for, where we keep inserting, but our basic action is to pull off the front. Right, so our normal, right, so our 2 basic actions. By basic, I mean common.
Is the lower numbers the higher priorities?
Yes, in this scenario.
Gotcha.
Basic actions are adding a data point and removing a data point with DQ. All right, so DQing from an array, once we make it circular, is going to be non-ideal, right? So DQing my non-circular array is going to be big O of n time, which is what we're doing with our lab while we're making our array circular. Just like some of you are losing points on that one because your array was not circular. Things need to go back around to the beginning. Right? Some of you were trying to do this DQ in a linear fashion by keeping the array as a fixed line where the next element is always at position 0, which means shifting everyone that's in line up forward, which is like a natural line, right? If you have a line at the bank and they pull the first person off the line, everyone literally steps forward. So everyone actually has to apply an effort to move themselves up the line. Whereas with the circular array, we actually take this, the kiosk moves closer to you, right? So it's kind of like when you're in and out and they got a big line of cars, right? They got someone outside of the board and they're coming to you. They're advancing the line by moving themselves up the line. So everyone in the line advance without actually physically moving, right? So they're doing that in more of a little circular array type manner with that mechanism. Right, so the moral of the story, correct implementation depends on what operations we support and which of those operations we expect to happen more than others. And just like we have with our searching, if I plan to search my data set frequently, but not maintain the data often, maintaining meaning adding and removing, then the effort of just collecting all the data, sorting it, and then opening up the binary search can pay results in the long run, as long as we can keep that structure as a long-lived object. Or long-lived is a very variable or vague term, right? That could mean minutes, that could be hours, that might need to be days before we get the benefit there, before the other costs start outweighing. So that's about that. All I have for that one. Questions we have at the moment. So any questions about stacks and queues? Are we doing all right with our push and pop?
How would you create a circular array? I'm having some trouble trying to understand that.
Right, so like we have here in our lecture notes from last time, right? This or this makes the array circular. Right, so back running off the end of the list, back goes back to the beginning. So this makes the first element the element after the last element in the array. The link to these on the syllabus. And this is the whiteboards link, which will bring you straight to the 2022 spring folder. And if you want to look at previous semesters, you should also be able to see them previous semesters. And I just tossed the links in the chat for the particular page that we're developing as we go along, but on the syllabus page, whiteboards.
Thank you.
Mhm.
I have a question.
Yep.
So is there any difference between in queuing from the front or from the back? Like at the end or at the beginning, I mean.
Well, the end and the beginning are sort of relative terms. So NQing happens at one end and DQing happens at the other, right? So we name the front and the back. Typically, we name the back of the line as the newest entry into the system and the front of the line the oldest entry in the system, because that's analogous to how we see actual lines. All right, so the front of the line is where we DQ from, and back of the line is where we NQ to. Yeah, so the purpose of the circular array is to keep our operations constant time. Because if we try to do a DQ with a non-circular array, so we will be forced to collapse the array, and collapsing the array is a linear operation. Right, so there's always the same amount of space. If we have a fixed size array and there's 5 elements occupied, right, we're half full. Whether the 5 elements are the first 5, or the 5 elements are in the middle, or the 5 elements are at the end, the queue still has the same amount of space allocated to it, and it's an array. So arrays are fixed size once you create them, or when you initially create them without doing a resize action, creating a new array, or extending the existing array memory, depending on how that works out. By making the array circular, by allowing the front and back pointers, not pointers, but right indicators of where we are, which part of the array is actually in use by the structure, it enables us to have constant time. Yes, so a question is, for an unordered linked list, insertion is BO1 constant time, because yes, if there's no order, if there's no data order, your ordering is going to be, I'm just adding everything to the head, or I'm adding everything to the tail, right? Which is like so if you're using a link-based stack, you're always adding to the head. Or if you're doing a link-based queue, you're just always adding at the tail. So you have a named pointer, you go to that named pointer, you adjust its link, and then you change the named pointer accordingly. When it's ordered, you have the finding part, right? So unordered finding is constant time, because we just go to the name pointer and we already are at the place we need to be. Whereas with the ordered structure, we have to get to that point, which means inspecting the data, comparing it to the new data point, and applying a loop. Yeah, for Mac, yeah, don't worry about EXEs, that's fine. Macs, they are creating an EXE somewhere. It's usually in like your users folder place, but that's fine. If I need to compile it and run it, I'll just use this website, because it doesn't force Visual Studio, Microsoft, unsecure, and all that fun stuff. Yes, I need the CPP is the file I have to have. That's your code, right? That's your work product. So when you're submitting lab or program, that is what I need to see things. Yeah, so on that subject, like labs, I just need the CPP and we're good to go. For programs, I need the CPP and I need just sample execution of your program. EXE is that's just evidence that it compiles. I don't strictly need it, because I won't run your EXE. I will run it inside of OnlineDB with my predetermined data points. So while we're here, a nice feature to point out. Yeah, it's really annoying to have to type in test data every time you run a program. So typically when you're having to do the same thing over and over, that's the job of a computer, to come in and save you from having to do the same thing over and over, and offer you a way of doing things in a repeatable fashion without having to repeat all the same work. So for this online compiler, if you switch from interactive console as the standard input to text, then you can go ahead and run the program over and over, and the CN statements would go ahead and pull from that text. I don't have any CNs in this particular application, so it's not pulling from it, but this is where it can come from. So if we had whatever here, right? So I can just go ahead and grab your code, drop it in here, run it. Does it match the output I'm expecting? That's good. Doesn't, all right, there's something wrong here. Figure out what's wrong, dock points accordingly for what's wrong. Otherwise, we can carry on to the next step of making sure it's a link-based structure as required, as opposed to using an array-based implementation. That sort of analysis. Okay. Let's see. All right. So we wanted to talk about the practice test. So let's bring the practice test up. Right, so test one, test area, as you can see from the practice, functional notation like we're talking about last time. Same questions, different lines, right? Binary search. Right, so I can ask questions about binary search. What's the precondition for binary search to work? The data sorted, right? It's an array based, as we're just talking about tonight, right? A linked based data structure storing the data set is not going to be well suited to a binary search. Right, this is saying how many values, right? Let's go through this one really quickly. Binary search, right? The key difference between binary search and linear search, we start at the first element and start our data comparisons. Linear search, being non-efficient, we switch over to binary search where we jump to the middle. So where's the middle? Middle is the beginning boundary, the end boundary, added together, divided by 2. So 0 and 7 divided by 2 is 3, because we have no room for fractional numbers and integers, and indexes are integers. So 46 is the first element we look at. So that's one data point. We see that 70 is greater than 46. So now our data set is here. We're looking at elements 4 through 7. 4 plus 7 is 11, divided by 2 is 5. Second data point we look at is 57. Next region, 6, 7 divided by 2 is 6. Look at 64, third, and then 70 is our fourth data point. Right, same idea, different data points you're looking for. Right, queues. There will be questions about stacks and queues. There will be writing code. Right, writing code typically going to be associated with an algorithm or a particular operation for a data structure that we've talked about. Right, so just write code. It says implement the body, right? Find last. So you can presume this code's already there. Switch to preformatted text so that things line up better. Right, for da 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 da, and eventually return some index or return -1 saying that we couldn't find it. Should always be a return value for a function. If you have a function that doesn't have a path with return, then there's something fundamentally wrong. Right? Basic algorithm operations, right? So we enqueued 10, then we had 5, then we dequeued, so that took away 10, then we enqueued 17, we enqueued 6, and the value at the front of our queue is now presently 5. Right? This is n times n. We're doing experimentation, right? The editor is not very well suited to this, so we're just doing n times n because n squared and n times n are the same thing. All right, true false questions, multiple answers. One thing I want to point out here with multiple answers, if stack push is the correct answer and binary search is an incorrect answer, the way this is going to, the way that Canvas grades this is it's going to take a correct answer away for every incorrect answer that you answer. So if you're hesitant on an answer, mathematically, you're better off to not put it if you're only half sure, because it's going to take away, right? So if there were 4 of these that are correct and you put these 2, you got half credit because these 2 are going to offset these 2 and it says you got 2 out of the 4 correct sort of thing. It's just how they implemented their algorithm for grading multiple answer questions. All right. Free-form answers, manually graded. So you'll not see these points after the answers are released on test day. All right, et cetera, et cetera, et cetera. Here, if I don't say write code, you don't have to write code if you want to write code. Well, I like to write code. Find the node I like the most, and then interesting spacing, update the links. Right. Doesn't matter. It doesn't say write code like this says write code. Writing a function. You're writing a function. Function is code. So this one says write a search function. Right. Search whatever we're calling it. Int star array, or if you prefer int square brackets array. I don't particularly care about syntax. I'm not grading you on syntax. Grading you on your algorithm making sense. Code that makes sense here. If you forgot semicolon, I don't care. Right, as long as it's not a fundamental thing that's just completely breaking everything. Right, right. So you goof and do a for loop. Right, parentheses in the wrong place. I equals 0, comma, whatever. I less than key. At least as long as the variable names. Right. I don't care that that syntax is wrong. It's a for loop. I understand what you mean. I understand where you start the first element. You're going to the key. Well, key is a bug, right? Because you should have gone to size, not key. So this is a type of bug where you'd lose points for because the algorithm is broken. Right. Compiler is not going to be able to check that your algorithm is correct. It's going to check that your syntax is correct. So we can rely on the compiler if we had one. We don't have a compiler because it's all through Canvas to fix us for those errors. So we will forgive those errors. But this, we have an algorithm problem because that should be going to the size of the array, not to the key. Okay, so a couple questions. If it's possible for something like the concept of a stack, I assume it means or queue, to have an option between FILO or FIFO. Yeah, if I were to ask you which of these data structures is the first in, last out, and you come up with the appropriate stack. Stack is FILO, whereas queue is first in, first out, because that's the intrinsic nature of those data structures. The practice test covers the materials. The formatting of the questions tend to be less like the practice test, right? So I'm not going to ask you the same questions necessarily, with the exception of like the binary search, right? I can ask you the same question here with just a different array and different values. True, false, those could be repeated. So I can ask a question like this, where I just give you different code, or ask for different line numbers ends in the sample. And yes, the test is timed. It is 65 minutes. Normally in class, it's a 60-minute on paper test, no book, no notes. But since they're a Canvas, you get an extra 5 minutes just to deal with this. Canvas isn't particularly clunky, but it's got little idiosyncrasies in it that takes a little bit of overhead. So do an extra 5 minutes for that.
Is this graded like the practice test? Is it graded on accuracy?
Yeah, if you put false for a true question, it's going to mark you wrong, sort of thing.
Oh, so it's like giving us point. It's like actually graded.
Yeah, so anything that's multiple choice, true, false, multiple answer, fixed number answers, that is going to be automatically graded. Some of them, I see here, I've got a regular expression behind this to actually grade this. So there's a couple of different ways it would have caught it for you. Use like a capital N that would have got through the regex, but
Are we supposed to know like all the information on this like as of right now, or will you like continue to cover it?
sorry, what was the question?
Like, are we supposed to know how to like do the entire practice test like right now?
No, we haven't quite covered everything. We're still talking about linked lists. I just want to bring it up because the drop date for this class is basically Saturday. So I want to give as much information up ahead of time for people who are trying to drop and get a refund. Forget what is the The other dates. Do. The right
I think someone
semester.
said that the refund date was yesterday.
Was it yesterday? I thought it was closer to Saturday. That's where we're here checking. Refunds. Okay, so it's past. Drop without a W is this weekend. All right. I knew this weekend was a particular date. So the refund Sunday. All right, so we passed the refund date, so dropping without a W. Like no pass, no pass. You have a longer window for that. I don't know how many people actually do pass, no pass, but things are going off target. What's an FRQ question? For a free response question, it depends on if it's essay format, no. If it's single liner of free form text, it depends on how I set it. If I can come up with a regular expression, then yes, it's auto-graded. If I don't think it's likely my regular expression will be reliable, then no. There's some fuzzy logic. Yeah, practice test still available. I'm not too sure what it show. Yeah, so it won't show you answers for free response questions because I don't have, it doesn't have auto grading for those. Those you won't see. The actual test is about 20, 25 questions. All right, because we do have test one rolling down on us here pretty soon. Right, you already see there's the answer to the first question, assuming I don't change the test between now and then. Don't. All right, you can see here function notation, big notation. All right, just so there's gonna be a lot of similarity between the test and the practice test, but not the same. In fact, right, so last time I gave the test, there were 18 questions. Not all questions are worth the same amount of points. Some are 1 point, some are 2 points, some are more than 2 points. The practice quiz is in quizzes. So you can get to it two ways. Syllabus, click on the item, the syllabus, and I put today's date on it. So it would be in context for day. Otherwise, all right, just go to quizzes and practice test is there. Yeah, the due dates are soft until Saturday. I'm pushing a day earlier than the drop date because Sunday is the last day people can use add codes. So if you're not going to be able to get all your work done, you don't think you're going to take the class, on drop. If you wait till the last minute, you're cutting off the window for other people to actually add the class. So that's why I'm doing the 5th, unless I already previously stated the 6th, in which case I messed that up. Let me double check. Due dates. See, 2/5. There we go. 2/5.
I have a question.
Go for it.
So for exam, we are going to take it in class, or we can take it on February 7th at any time.
We will be taking it during class.
Oh, okay.
Typically, we get out of the way at the beginning. We used to have the class vote on it, but the voting has been pretty consistent. They want to get it over with and done and not pollute the mind with a whole bunch of new information that's not going to be on the test. So usually by 6:10, we will start taking the test. Basically, what I'll do is I'll take 30 minutes of lab time and 35 minutes of lecture time, and apply that to the test window. And then after the test is done, carry on with other things.
And are we going to a breakout room, each one of us, or
Sorry, break what?
are we going to like separate breakout room to take a test?
No, you won't go any rooms. You will just message me directly in Canvas, in Zoom during the test if you have questions. So if you have a question, what does number 1 mean? Or what?
Thank you.
So that's why we take the test during class. So if you have questions, you can message me directly. Find that I've got a bug on the test. I can make an announcement while we're taking it so people can be aware of that bug. Yes, you have all of Saturday before late penalties start to apply. Yeah, you can use notes. I'm not using Proctorio, any of that stuff. In theory, that we're online in a temporary fashion right now. This is not a fixed online class. This is an in-person class where in-person is just via Zoom instead of in District 109 or wherever the class normally was 2 years ago. So you have advantage and disadvantage being online. Because normally notes are not allowed. Okay. Let's see. Let's switch over to the labs. All right, linear search. I don't think I don't think I need to talk much about this one. Looks like 20 of you are still 56, almost 20 of you are still not yet have done linear search. So you want to make sure you do that one sooner rather than later. IO. There's lots of different ways to fry the egg here, and it doesn't much matter how you're frying the egg. I don't care. It's not really an algorithm or data structure related. It's just foundation for doing things. Hello, right? I like 3 potatoes and 0.5 turnips, whatever. The key is you need to be able to split things up. And then work on each one. And every language is going to be definitely different on this one, on how you actually do this. Some languages being easier than others. Number times 2, double number, whatever. The point of that being, we recognize it's a number. If it's not a number, we just spit the word out. All right, so string stream is our C++ equivalent, split, common amongst other languages, right? It's 3 was doubled, 0.5 was doubled, handles negative numbers. Some of the things I've noticed is negative numbers not running very well in some of your applications, and program 1 is going to be a calculator. So negative numbers, fractional numbers are things that are going to be valid data points. So be careful on that one. All right, again, string stream in the files section. You can look at strings. Let's see, string streams. Brief example, right? Get your string, get from the keyboard, build a string stream, and then string stream overloads the extraction operator, so you can go and split it up. So it's just a matter of testing if each word is numeric or not. And that's all just C++ language. So that's why we're trying to be as language agnostic as we can in the class. We just happen to be using C++ as the implementation of our code. Once you have your data structure algorithm, it should pretty much one for one be translatable to every language that supports those language constructs, objects, arrays, pointers, that kind of stuff. Right, so if I were to go write a Q class over here in C#, I can take the code, right, and more or less take this code and drop it over in C++, make our syntax changes, and then it's good to go. Structurally the same. The annotation is going to be the same. The algorithms are going to be the same. There's just syntactual differences. Right, things like getting input and output, that's just going to vary from every language to every language, because every language that I've ever seen has their own way to fry the egg. That part, however you want to dice it, if you want to implement your own algorithms to dice up the users, or some of you had custom parsers, right? Double parse, string, word type thing. And you had your numbers list, for example, either as an array, right? 0, 1, 2, 3, 4, 5, et cetera, et cetera, et cetera. 8, 9 type thing. This is one of the places where you have bugs. Right, it's for each char letter. And word type thing. Right, if checking against the list is not found, then we found something that means this is not actually a number. Otherwise, we say, yes, it's a number. 0 indicating it was a number, do whatever we're going to do type thing. But you're not accounting for negative numbers, you're not accounting for decimal points. So just be careful if you wrote your own custom parser. These are things that are baked into string stream, and feel free to use string stream. If you haven't used string stream before, that is the go-to for string parsing in C++. And that's who you want to use. If you want to fall back on stirtoc, feel free, right? That's the C go-to for breaking apart strings, also known as tokenizing. Okay. Okay, sorry, 1 second. Okay, so our other labs. All right, dynamic arrays and simple arrays. Right, so simple arrays being exercised stack-based array, which means if you just go say int array in a size in C++, that means it's stack allocating the array. And depending on your compiler, that literal that's storing the value 5 needs to be a constant, or some will say it doesn't have to be constant, they'll work with you. Again, if there's no submit button, that means there's nothing to actually submit. You just want to make sure you know how to do this, because it's something you might be coding on the test or on as preambles to other labs. All right, so for our dynamic arrays, when we're seeing dynamic, we're meaning heap allocated memory. So when you're doing this, you're going to want a pointer in the new keyword. Pointer in the new keyword will heap allocate the array. So the pointer is on the stack, the actual array contents are on the heap. And heap's memory is always going to be accessed via a pointer. Any questions about the two arrays labs?
Sorry, could you remind me of what's the heap?
Remind you of what?
The heap?
Heap's an area of RAM that is allocated to the application for dynamically allocated memory. Right, so talked about that really. We'll talk about that. We'll take a break and then we'll talk about that one after the break. So we'll get to that in a second. Then our other arrays and exercises we'll talk about later tonight. So let's go ahead and we'll take a 5-minute break, and then 10 minutes, try to, those of you behind the labs, try to catch up on the labs. Those of you ahead in the labs, go ahead and keep pushing through the other labs. We'll keep talking about those again later tonight as well. So we'll come back, let's see, at 20 till. So 7:40, break till 7:40. So break and lab. So I'm going on mute. If you ping me in chat, I will respond to you in the chat. Otherwise, I'll be off audio. All right. I saw your link in Discord, so I went ahead and added that. To the modules section. Stacks, queues, lists, array, Java. Okay, Java, C++, pretty close. That's not bad. Yeah, we'll get to begin into recursion before too long. There are things here that we don't go over. A lot of these things are lining up with what we're talking about, which is always good. All right. Right, heap versus stack. Right, when your application launches, right off disk, load in memory, and everyone can hear me, right? I'm not talking on mute. Sound check. Lose anybody?
Yeah, we can hear.
We're still recording. Is that still working just fine? Guess where I turned the live transcript. Yeah, that's going. I turned the live transcript on earlier. Apparently I didn't click a second button. Okay, live transcript is now on. Right, so when the application is loaded up, it's given memory, right? Task manager, whatever is running. This memory just represent a portion of the RAM. It's being allocated to the various applications. Your application being something that would be running. And there are two primary areas of that memory, the stack space and the heap space. There's also global variable space and other things, but that's beyond what we care about. Stack, so we get our functions, local variables, another stack frame overhead. Right, these frames live as long as the functions are on the stack frame. Heap, this is for dynamically allocated items. I forgot to share the link. Do that. All right, so new malloc, calloc, realloc. And they're all dealing with this address space. All right, and these are longer lived items. Live until we explicitly send them away. Right, at least in C# or C# in C++. I'm sure there's probably a good website for that versus stack memory. Let's see, Geeks for Geeks looks good. All right, so if you want to dig in further on that, you can check that out. The key thing with the heap memory, it's a memory address that is going to be required to track anything that's created on the heap. All right, 1 second. All right, cross-checking. How are we doing on our big O notation, right? Worst case analysis is our default. Time complexity for how complex the algorithm is or how costly the algorithm is. How we do with the circular arrays we talked about last time. It's basically take a line, take a string, and tie one end to the other end. Now you've got a circular string. Same idea with the array, where after the last element is the first element, or before the first element is the last element in the array, however big you made the array. Right, you can do the same thing with linked lists. If you link the last node back to the first node, no, I should say circularly linked list. Okay, let's talk about reverse bullish. All right, so reverse bullish is a mathematical notation. We're used to an infix notation for the operator. The binary operators sit in between their operands. Reverse Polish is a postfix notation where the operator sits after the operands. This notation works well with the stack data structure. And so the way we handle a postfix expression is we repeatedly read a token. That is going to be either an operator or an operand. If the token is an operand, the token's operand will push the operand onto the stack. If the token is an operator, we'll pop two values from the stack, operate on those values, and push the result. Right, so note that the operand order is maintained or is operated on in the same order in which they were read in. So here's an infix expression. All right, 1 plus 2, and that equals 3. Equivalent postfix would be 1, 2 plus, and that equals 3. All right, so read 1, push 1. And that gives us the stack state. One on the stack. Read 2, push 2. So we go ahead and add to the top of the stack. Notice that the top is to the top of the page. Then read plus, operate. We'll pop the right-hand side, operand, and then the left-hand side, operand. All right, so we have left-hand side equals 1 plus the right-hand side, which equals 2. Result of which is 3. Then we'll push 3 onto stack. All right, so 1 and 2 were popped off. And this is the final state of the stack. 3 is the final answer as the only value on the stack.
Wait, why did the 1 and 2 like get popped off?
Because we read an operator.
Oh, okay.
So we read the plus. So we'll go ahead and do a pair of pops. To add the pop word there. All right. And then we use those values to operate upon using the plus operator. And that gives us the 3, which we'll push back onto the stack. So the advantage of postfix is there is no operator precedence. Plus, minus, divide, multiply, etc. are all treated the same, which is not the case for infix. All right, so we have an infix expression, right? 1 plus 2 times 3, all right? Because of operator precedence, that's 7 as opposed to 9, right? We don't add 1 to 2 to give us 3 and then multiply by 3. We have to just take note of this data and just track on to it later. So like older calculators, right? Way older calculators, you know, before my first calculator, they use a reverse Polish mechanism to do the work, because maintaining a stack in a small little calculator system there, you know, how many bits those calculators had, it was something easily done. Maintaining complex expressions, that's a different story, right? Just think of a four key or 4 function calculator, right? You got your digits and you got plus, minus, multiply, divide, right? You can't type 1 plus 2 times 3 and get 7. It's going to give you 9. It's going to calculate the expression it already has as soon as you hit the next operator or the equal sign, and then give you that intermediate result, and then proceed with the next data point. And it's just going to keep basically 2 values at any given time. What's going to be on the left-hand side and what's going to be on the right-hand side of the operation you're going to do. So required, if you had a written down expression, you had to translate it yourself. The human had to impart the operator precedence because the calculator itself wasn't able of doing it unless you actually had a reverse Polish calculator, in which case you would have the expressions in reverse Polish, put them in there. All right, so our equivalent postfix expression. If I could type, that's okay. Google will fix it for me, right? I guess I didn't actually spell it wrong. All right, so we'll maintain the same order. The first thing that happens is the multiplication, and then we'll do the add, and then we'll get the same result. So let's go ahead and show that. State, and then the stack. All right, so we're gonna have various states of our stack: 0, 1, 2, 3, 4, 5, representing different points in time. All right, so we read the first value. That's a 1. So we'll go ahead and push it. Read our next value, operand again. So that gets pushed. Read the next value. 3 is an operand. So that gets pushed onto the stack. And we'll get to a multiply. All right, so 2 and 3 pop off. All right, so our stack state is just the 1. After 2 and 3 are popped off, multiply 2 by 3, giving us 6. Push that onto the stack. The next thing we read is a plus. Pop off 2 values, the result of which is a 7. And let's try that again. Single click, okay. Oh, that's just lovely. It's always fun to have a 3 pixel click space. Yeah, so the postfix, we're just doing binary operators. you can, if you had operators that would supported more than 2 operands or fewer than 2 operands, it's the same idea. If it's a unary operator, right? So if we like have an exclamation point to represent an inversion or a negation, that would just do a single pop to do the operation. If you actually had a ternary operator, then we need to pop 3 values. It just depends on the operator.
Can you kind of explain like the postfix expression? Is it saying like after 1, 2, and 3, then you would just add the numbers?
Right, so post, just right, Greek for meaning after. So the operator is after the data points. So in order for an operator to work, data points first have to be seen. Then the operator pops those values, operate on. And the reason we talk about it is because it's a simple application or algorithm that makes use of a stack. Right, or a practical example being the runtime stack, which is baked into the application runtime, and not really something we want to really dig into the complexities of that. Right, so the algorithm is we're going to break apart the sentence by white space, just like we did with the IO lab. If it's a number, it goes on the stack. If it's not a number, we'll do something else with it, in which case we're going to take data from the stack, apply the operation, and then push the result back on top.
Oh, okay, that makes sense. Thank you.
Okay, so let's do a bigger example. Make use of multiple operators and make sure that they're not commutative, so we get the operators in the proper order. So 1, 2, 3 minus 4 plus 5 times 6. Then we'll do a divide. Let's see, what's that, 4. And finally a multiply. Let's see what we get. In fact, let's just copy this table. And let's see if that's enough. All right. So we read 1, push it. In fact, let me change my numbers a little bit here so not that close to the stack state. So I go 4, 7, 4, 7, 6, 2, 3, and 5. Okay. So the first thing we read is a 4. That's non-operator, so we push it. Next thing we read is a 7. That gets pushed. So we read a 6. That gets pushed. Then we read a subtraction. So 7 and 6 are popped. 6. Right, so basically, we're doing this operation. 7, 6, and subtracting. We're taking 6 from 7. We're not taking 7 from 6. That would be a mistake. 4 was still in the stack. The result of 7 less 6 is 1. So we push that result 1 back on the stack. Next thing we see is a 2. So we push that. We get to a plus. 1 plus 2 is 3. So we push the result there. Next thing we read is another 3. So we have 2 3s on the stack. Then we do a multiplication. 3 times 3 gives us a 9. And we'll read a 5. Then we'll do division. So 9 divided by 5 is 1.8. My brain's working. Feel free to check my math. And then we'll do a multiplication for what, 7.2. And the expression is ended. We have a single value on the stack, so the expression was well formed. Just like with infix notation, there's going to be one operand more than the number of binary operators that we have.
Can the stack get bigger than 3?
Sure. Stack can get as big as we've allocated for the stack. I only needed to make mine 3 because that's big as it needed to be, but there's definitely clearance, right? Even if we're using an array, we fix size it to say 10, and we get up to 10 high. If we're using a link-based stack, then it's as much heap space as we can get. Right, and if we're doing a general application of a stack-based class, we're probably going to be link-based. That way we don't have to do the complexity of we're at capacity, we need to resize the array, or we're way under capacity, we need to shrink the array. That is one of the intrinsic benefits of a link-based stack, is pushing and popping is not a lot of code, and you can more or less indefinitely push, and you can always pop as long as there's something to pop from. And of course, nothing is infinite in a computer. You're still bound by however much memory the system will give the application. All right, so 1 second. So question, were plus and 3 plus supposed to happen on state 5? Yeah, so we had 1 and 2 on the stack, then we had a plus. So that yielded this 3. We read another 3. And then we got to the multiplication. So the 1 plus 2 gave us this 3. And then we pushed, I guess let's do some color coding here. Let's do operational result. So this one, right, that was a result that was pushed back on. So orange are operation results pushed back. Right, then we had the 3. That was a pushback. And then we had the 9. We pushed back onto the stack, and then 1.8 operations. And an operation. Right, so our black ones 4.7, 4.7.6, those were just regular read push. And that was an operation push. It was carryover from previous stack state. Right, then we have carryover from stack state, additional read push, and then operations. Why isn't the 2 in stack 3? Because I was doing one change at a time. So I could very easily all draw this on the same stack, which just shows harder. These are states, right? So these are just points in time. So the next point in time is after we do another read, and after that read, we do a push.
That was sort of my question, was because I think like the subtraction happened on like the 3rd frame, or I guess 4th, but and
Right.
then the 2 was pushed on to the next one. But then for like the 5th state,
Right.
I think that the like addition happened and the 3 was also pushed on.
All right, let me make sure I didn't overload things here. All right, so we got push 4. Push 7. Push 6. All right, operate. And we push 2. Operate, I see. I got both of them in the same frame here. All right. Excellent. Observations. So we had 4 carryover. Fix that color in a second. That was the push. Carryover. And we'll get rid of that one. And there we have one state change. All right. And I did the same thing here. I just kept on loading up here, didn't I? All right. So 4 carryover, 9 carryover, 5 is state change. All right. All right. So let's see. I think we got it better now. Now we're definitely more isolated. Okay. Yeah, the states are just points in time. And some of the times I was doing multiple operations between my state changes, so I was just not wholly consistent with representing the states. All right, if I were to turn this into a test question, it would be along the lines of, right, what is the top of the stack after the first multiplication type thing, right, which is would have been a 9, or what is the bottom of the stack at any point in time for the final answer in this situation here, right, which is just the 4. Yeah, right, so this is just object state being something that changes as the application runs through the algorithm. All right. Let's dig into some code for a little bit here. Okay, instantly linked list. All right, stay linked list. This is our visualization of a node object. There's an area in the object that's going to hold on to the data. And then there's going to be a link section. Here, we're just being simplistic and just saying the data is an integer, right? If you better way, of course, would be make templates and BT info, and then you can create a list of whatever data type you wanted to. Books, cars, planes, trains, automobiles, whatever. We don't really care what the data is. We care about how we are organizing the data. So we just keep things simple and have them be an int. All right, our next pointer, which is our link, its data type is the same as the data type of the class itself, right? It is a node data type. So like I mentioned last time, it's a self-referential type. I could create a node and I can set the next equal to the node that we just created. We're doing okay with our data section, right? Data link. This is our actual object state parts of our node. The last bit, which I have in our sample code, is an overloaded constructor. Overloaded via the default assignment of the pointer. So if we create a node with just the data point, we'll set the data point to whatever we passed in, and the pointer will be null. If we call the constructor with an existing pointer of the node type, it will just set the next pointer equal to that existing node. Next up, we have our singly linked list class, which is going to make use of those nodes. So the way I'm presenting to you the linked list code is I'm keeping our concerns separated, which is a proper object-oriented programming practice. You want your types to be as small as possible. It's entirely possible to do all this code inside the node class, have all the logic be inside the node. I see students do that on a fairly frequent basis. You don't want that kind of tight coupling in your code. You want to keep things as separate as possible, right? This code is pretty simple for the node class. There's very little it can do. It holds a couple of data points, it has a constructor, and that's the end of the story. It doesn't have to worry about that it's in a singly linked list or that's part of a queue type or a stack type or any other data structure logic. It is just its own little entity. Our singly linked list class, because this one's a little bit generic, we're going to support both the head and the tail named pointers. Like we saw last time, right? White space is somewhat arbitrary. Head and tail are both pointers of our node type. Just the default constructor, which is going to set everyone to null, just so we're nice and explicit here. I've seen different compilers, different students have problems by not including default constructor where it's initializing pointers to some other arbitrary value. So when they try to do null tests to see that if we're at the end of the list or the list is empty, things don't work out too well. So make sure you put your default constructor in there. Don't rely on the compiler to emit code that's going to initialize things for you, because in the C++ land, that's inconsistent. Deconstructor, all right, nothing very special. It's just going to go ahead and destroy the list because it's always bad to leave memory leaks floating around the code. We have a temporary pointer, which we initialize in the body. And while the list isn't empty, we go ahead and grab on to the next data point, free up our memory with the delete keyword, and then slide the head down. The head just works its way towards the tail, and eventually pointer will point to head next, and there will be nothing after that node, so pointer gets set to null, and then the head gets set to null, and then the list is back to an empty state. Right, so we know that the list is empty when the head and null are the same value, and that's exactly what our isEmpty function does. Tests the head against 0, aka null, and returns back 0, 1. This was when long before bool was a little bit more supported, so it's still just as an int. All right, add to head. And just move the comment over here. Basic operation. And we'll limit the comment. All right, so our basic operation is create the node. Whether the list is empty or non-empty, there's 1, 2, or 20 nodes in the list already. First step is always to create a node, and we're just going to call it temp. Set the data inside our node, and next thing we want to set is the next pointer to head. So the very first time we call add to head, head is null. So the very first node we create, its next pointer is going to point to null. It's not going to point to anything. And then we'll make the head the same as that temp pointer. So after we've gotten through these 3 lines of code, the list will be the one node, and head is pointing to that one node. Because we also have tail. If the tail is null, which means the list was empty before the insert, we're going to go ahead and set the tail equal to head, or we're going to set tail equals to temp. Same difference with this version of the code. And we have our one node list. Add to tail. All right, 2 branches, 2 basic scenarios here. We have an empty list or we have a non-empty list. The empty list is covered off right here. We create a node, set that to the tail, and we set that to the head. And we now have a list that has one node in it, and head and tail are both that one node. Our non-empty scenario where the tail is not equal to null, or we could just call this empty because it would have been the same logical thing. We're going to go ahead and create the node. This node will have whatever data point we passed in. Its next pointer will be null per the constructor. And then we will link that node to our existing tail with its next pointer. Last thing, slide the tail over so that the tail pointer is pointing to the last node in the list by saying tail equals tail next. So have the tail point to the thing that it's presently pointing at as per what we just did on the previous line of code. Questions before I keep scrolling? All right. Deleting from head. This function has a precondition. The precondition is that the list is not empty. If the list is empty, head is null. If head is null, this is a null reference exception because you cannot go to the info of something that does not exist. So bear in mind the sample code has a precondition that the list is not empty, otherwise it will explode at runtime. Null reference exception being the billion-dollar mistake. Let me see if I can find a link for that. You can read up on that one. Billion-dollar mistake. Let's see, we can, there we are, number one hit. Just toss that into the chat, read up on that one. Null references, and I'm sure it's probably growing to the $1 trillion because a null reference exception is a very common error. Presuming that there's data when there isn't, the fundamentally flawed presumption. But otherwise, assuming we can actually have something to delete from the head, we have grabbed the data, set it aside so we can send it back when we're done. Set a temporary pointer to the head so that we can free that memory up afterwards so we don't have a memory leak. And then we have two scenarios. Either we're going from a one node list to an empty list, or going from a more than one node list to just a one smaller list. Right, so 138 has two scenarios where this could be true if it was a freestanding line of code. Head and tail are both equal when the list is empty because they're both null. And head and tail are also equal when the list has one node in it. The empty list scenario is covered off by the fact that there's a precondition on this function or a bug, depending on how you want to spin this. Because if there was an empty list, we would have exploded before we get to line 138. So we're not worrying about it. Otherwise, we set our pointers to null and indicate we've gone from a one node list to an empty list. We can clean up our memory and send the data back when we're done. Otherwise, head equals head next, whatever data point we're pointing at. So if we have, let's do some drawing. Say we have our list like so with 4 and 5 on it, and head, right, would point to 4, and tail would point to 5. Head equals head next. Head next is 5, so head equals head next says we're now pointing to 5. We're going to forget about 4, and then we can delete temp because temp is pointing to 4. So when we get to line 143, we can say this memory is no longer needed. Then head and tail are both pointing to 5. Delete from tail. This one is going to be our expensive operation, or one of our expensive operations, because our objective, should have left my drawing up there. And say we have 4, 5, 6. Yeah, it's a terrible looking box. I should just be using shapes here. All right, where head points to the 4 and tail points to 6. In fact, let me just know why it's green. Let's change my color and let's make this a little bit easier to see. All right. Heads over there, tails over here, and they're pointing to nodes. And they have arbitrary data points. Don't much care what the data points are. If we want to delete 7, right, our objective is to make it go away. The 5 node needs to point to nothing, just as this one's not pointing to anything, so there's just no arrow being drawn here. But I can't get to the node to the left of tail from tail because this is just a one-way link. In fact, let me make these with arrowheads. So in order to get to the 5 node, I have to start at the beginning and we need to work our way down, right? So we start at the head and we iterate until we're 1 before the tail so that we can manipulate that pointer and set it to null. All right, so as soon as we get to that scenario, right, again, like before, precondition, if it's an empty list, it blows up line 150. Otherwise, it's a 1 node list, in which case we delete the head, we set the head and tail to null, and we're done. Otherwise, it's a 2 or more node list, in which case we need to do some iteration. And all that here is in the for loop. This is the entire loop. Note the semicolon here at the end. Put this on the next line. It doesn't much matter. It's just white space. We start at the head. And we look at the next pointer. See if it's not the tail. All right, so if it's not the tail, temp equals temp next. All right, so it's possible temp next is already null. If that was the case, we would have been over here in the head equals tail scenario because there isn't more than 1 node. Otherwise, we're in the 2 node scenario. And if it's 2 node 3 and 5, temp next is equal to tail and the looping stops, and temp is at the head. Which means we can go ahead and kill 5 and be done with it. So the first time through, temp gets to 5, we delete the tail, make tail temp, tail next is equal to null, so we don't have a dangling pointer. Dangling pointer being one of those other bad things that applications might have where we forget to null out a pointer that at one point in time was pointing to an object in memory, but that object in memory has since been deleted. And something else may be living in that spot. Could be another node, could be something else entirely. Second time through, we have 3 and 5. All right, so all that is gone. Kill a little bit more than I meant to. Heads over here. Now our tail is over there. And whatever our numbers are, 3 and 5. All right, so temp is equal to head. Temp next is the tail, so temp stays right where it started. So we go ahead and delete the tail. See if I can erase this without being overly too big of a boxes. All right. Just exit out manually. We delete the tail. Tail equals temps. Now tail points over here. And tail next equals 0. So now we're not pointing at a node. How are we doing with the syntax and code here? All right. draw pictures when working on the code. It's the best way to try to correlate what's going on inside the machine memory to what the code is trying to do. Delete node is the generic version where we're deleting it anywhere inside the list. This one's doing all the proper checks, making sure that there is actually a list to delete from, checking the scenarios where we have a one node list and that node is where we're deleting from, or we're just deleting from a list that has more than one node and the head is the scenario. But the common situation is we're going to be somewhere in the middle. So like we did before with deleting from the tail, we're going to iterate. And this time we're going to track a couple of pointers because the temp node is the one we're going to want to delete at the end. And the predecessor of temp is the one that's going to be just before temp that we're going to want to bridge over the gap. So if we have a list that is the equivalent of the dot operator in Java and other languages like Java, it is the dereference the pointer and field operation. Because pred and all dynamically allocated objects C++ are pointers, right? Pred's a pointer, temp's a pointer, and a pointer is just a memory address. The memory address needs to be dereferenced to go to the actual object before you can work on the fields of that object. So the arrow syntax is both a star and a dot, all wrapped in one. Right? There's the equivalent star pred dot next. Right? It's the equivalent, but this is just heavier syntax because the dot operator has higher precedence than the dereference operator. So they introduce the arrow operator. All right. 2, 4, 5, 3, whatever our data points are. And again, the first one's the head, the last one's the tail. Say we want to delete 5. All right, so we've got the predecessor over here starting off at the head and temp starting off at head next. We have a check to make sure that we haven't run off the edge of the list. And we have a check to see if we have found the node that we want to remove. All right, 4 is not 5. So we're going to go ahead and shift both of the pointers. Temp moves over. And predecessor also moves over. And then we check again, temp is not null. And temp info is the data, so we go ahead and our looping stops, right? We've got this empty body loop. And then 2 scenarios once we get to this point. Either temp ran off the end because we're trying to delete 11, and 11 is not there, in which case temp just kept on going into the void, or we did find who we're looking for. So if temp got to the end of the list, there's no actual node to delete, so we're done. If not, we found a node and we want to delete that. So we're going to go here and bridge the gap. Predecessor next equals temp next. Temp next is 3. Predecessor next is this arrow coming from 4. And we're going to go ahead and bridge that gap. Make sure we're not deleting the tail, because if we are, we need to back the tail up. And then we can clean up memory by deleting temp. How we're doing with our pointers. Pointers are just the best, right? It's best to just think of them as reference type variables. Most languages just use the dot operator. Just the dot operator just takes care of it. Right? It's just how the language implemented the operator dereferenced. the reference and get you to the fields. Problem with C++ is, right, you can create local nodes, right? A local node means it's lovely stack allocated, which affects its lifetime. Right, so yeah, it's best to avoid trying to do that type of stuff. In fact, it's trying to yell at me here. No default constructor, right? Fine, whatever. And this is a practice you want to get away with because it's just C++ is an evolution language from C, so some of the things are a little bit weird that you don't really see anymore in newer languages. Is in list, right? This is a linear search. We start at the beginning, look for our data point, and if we find it, we return that we found it. So if temp goes to null, we didn't find the list. Temp is not null, we found it in the list. We already had the data point, so we don't care what the data point is. There's no index to return. So either we have the data point already or we don't, which might be important for like duplication. If we don't allow duplicate values to be in the structure, we can scan it, see if it's there already. If it's not there, we add it. If it is there, we say, we've already got it. Thank you. Carry on. All right. All right, so you can run through this code and see things going on here. You can see the testing of it. Very, very brief. Let's go ahead and take another 10 minutes. We'll do a 5-minute break. And then 5-minute break / lab time. Go ahead and swing into those labs. Hopefully people have turned a few more things in, but otherwise I'm going to go on mute, off audio, and ping me if you have questions in the meantime. We'll be back at 18 till. Fold in, back at All right. Anyone with questions before the train keeps on rolling? How long should you stay on the track for? Should you try running away from it, towards it? Zigzag, dodge, duck, dive, roll. And run towards the train. Yeah, that way you can get a better view of how the train works. Let's see. Where is my folder? There it is. Depends on how big the train is, right? If it's a 1/32 scale model or whatever scale models you go to, sure, no problem. Okay, last item. The test one, Nina. Doubly linked list. This is very much like singularly linked list, except our node structure now supports 2 links. This can be applied in different ways. Common use of the second link is to have a pointer to the node to the left, in addition to the node on the right. The double link list, you'll want to have 2 named pointers representing each end of the list. If the data is sorted, you can print out the data in ascending or descending. Ascending order by starting at the respective end. All right, so as the list gets built, similar ideas we had before, except we'll have links going both ways. So we'll just make the arrow double-sided. Representing both directions. Again, name nodes like before. A head pointer and a tail pointer. The node structure looks much like our singly linked list, where we just go ahead and add in add in this one additional part. So you go ahead and go grab the singly linked list node class, add in one more pointer, name it something, and now you have a doubly linked list node. All right, so we just have the extra pointer to deal with as we add or remove nodes from the list structure.
It doesn't matter if you're pointing to next or pointing to previous, right? It just matters that you're pointing to one of them, correct?
Well, you wouldn't point to previous or next. Next or previous would point to a node,
Right.
right? Because this whole node, okay. Lost my annotate window. Let's hide on the top of the one, right? So, right, this entire node is the object. Right, so the memory address, of course, represents the very left boundary of the object, and then the entirety is the object. So if someone were to point at this node, we just point at the whole object. And then next and previous, if this was a circular doubly linked list, could point back at the node itself. More commonly, as we have here, right? So this edge is my next pointer, and this edge is the previous pointer, and it's pointing at the object. Right? So another way I could draw this, right? It's pointing at the whole node, and this edge is pointing at the whole node, meaning it's just storing the memory address of the node on the left. So the memory address stored in this part of this node object is the same as memory address being stored at head in this particular list. And the same would be true over here. The memory address that tail is pointing to would also be the same as the memory address that this next pointer is holding onto inside its memory location. Because if we look at
So you're pointing
Right.
back to the object, to the data.
if we look at the actual object in memory, right, we have some sort of OX1294, whatever. FAF, let's say the data was 15. And then we have another point here, OX12787, whatever. F. This would be the actual object. A pointer, an integer, and a pointer. Where this refers to some other object in memory, and then this refers to some other object in memory since they are different memory addresses, right? Say that contains 7, that contains 11, whatever the data point may be, right? If this memory address of this box, just call it whatever, CCCC, no, let's do Fs. 1, 2, FF, FF, since F is 15, right? This will be the value stored over here. Right, where this whole box is in memory, and the same thing over here, since this one's pointing back to it. Right, this one is pointing back to this same object. Right, it's doubly linked, and we'll say this one's the head, this one's the tail. So that's a null there, and this is a null here, assuming top one is the previous, and the bottom one is the next. Because that's all pointers are just values that hold memory addresses.
Oh, okay.
Right, so if you dereference that pointer, so if I'm in the head and I say head next, right, text. If I do cout, head, next, data. All right, so head is this node because the value inside head is whatever the memory address of this node is. We then dereference that pointer to get to the next field, which then reads in this 12FFFF, which we then dereference to get to its data field, which then takes us to the 15, right? So this would output 15 to the console.
Okay, thanks, Professor.
Mhm. Yeah, this is one of the tricky parts with data structures. Dealing with these pointers, which is a memory address, and human doesn't consume a memory address well at all, which is why we draw it, right? This, instead of just dumping memory addresses in these objects floating around, we'll draw the arrows out, say, okay, this memory address just refers to this object over here, and that one in turn, because these are links in the chain, returns points to the next one. Does the left of head? Yes. So left of head is null, and the right of head of tail is null, which I called previous and next, which we could have easily called left and right. Right? Their names, variable names, and variable names, of course, have a degree of arbitrary inherent to their nature. Right? We could call them lesser and greater if this is intended to be like a sorted list, where the one to the left is lesser in value, one to the right is greater in value. Right? Using a name that makes sense to use way to go. So, right? Don't use the names in my code. Use names that make sense to you when you write these structures, because a helpful variable name can be helpful beyond just being a good name. Right? If you don't like head and tail are certainly names that are replaceable. Right? Head could be called lowest, tail could be called highest. Right? It's all full in the theme of a lesser, and yeah, you can call them Tom and Jerry. Right? Roadrunner and Coyote if you want. Put the Coyote on the left because he's always behind the Roadrunner on the right. Right, so all the code mechanics are very much the same like they were with the single linked list. We're still here. Here we are, double linked. Download this. So pretty much take that other code file we just looked at, do a little bit of renaming and adding. Right, I changed the nest to a D over here. Added in the backlink to our list of fields, right? Added a little extra link to the box over here. And then we added in an extra overload, right? So now there's 1, 2, 3 different ways that we can call a constructor. A required integer parameter, an optional last pointer node, and an optional next pointer node. So if you're not familiar, if you don't familiar, you've never seen default arguments or optional parameters. If I call the constructor with 2 arguments, the first 2 get filled up. If I call it with 3, then all 3 get filled up. All right, so the extra line of code for the last pointer. Otherwise, very much the same node class as we saw before. Doubly linked list node, similar in the fields here. I have a head and a tail, this time with a DLL node type. Constructor, pretty much the same as we had before. Deconstructor, pretty much the same as we had before. Is empty, the same. Add to head is mostly the same. Just want to make sure that we're tracking everything, make sure that the head is properly set. Right, the overloads are handling a lot of the logic here, but so a lot of the codes are similar. I'll let you on your own go through it. It's very much copy paste and small tweaks from the previous code file. And that's pretty much it for that. We do also have the sorted version of the class. Right, it's just we have the extra links to keep track of. Like before, We need to get into position step by step, right? So as always, when you're adding a node to the list, you got to create the node. Whether it's going into the front, the back, or the middle, might as well do that one time instead of having it in all the various branches of creating a node. Get the temp going on, and if the list is empty, make the list. We're done. Kick out of our function. Otherwise, iterate down. See if there's someone after the node we're looking at right now. Do our data check. And if we need to keep going down the list, keep going down the list. Next and last pointers. So when we are building the bridge, right? So say we are somewhere in the list. Where we had 15 and we had 40 and we're adding 31. So at the moment, 15 points to 40 and 40 points back to 15. And we'll have a temp node somewhere around here. It could be either one because we're doubly linked. Our newly created node 31. 31 has 2 null pointers when we constructed here, right? Line 304. Created the node. I didn't set the previous or next pointers, so both pointers are null. When we're building this bridge, we want to set null pointers first. Okay? It doesn't matter if we do 31 previous to temp first, or we do 31 next to temp next first. Either way, we're setting null pointers, so that order doesn't matter. So we just want to make sure we do these first and or second. Right, that's the half of the bridge. Now these 2 links need to be shifted, and again, these don't matter too much in the order, just depends on how you're getting to them. That order can matter slightly. Right, because right now temp of next is 40, but we're going to want temp of next to be 31. So it's just a matter of how we get to this link here, because we can say temp of next of last. This is where the syntax gets really fun. Right, 2 different ways of saying this. All right, so if we want to manipulate this pointer first, we can say temp next. Temp next is 40. Its previous pointer is this back arrow, and we want it equal to our new guy, which I'll just say 41. And so another way of writing this, we can say 40 previous. Right, logically, you can't code 40 because 40 doesn't exist, but 40 previous equals 31. Right, because temp of next and 40 are both the same thing at this point in time. So we'll draw this as a replacement. This edge is no longer going back. And then we can go ahead and say temp, which is 15. Next pointer is equal to the new node, which is basically saying the same thing as 15 next equals the new node. So we'll go ahead and set our other pointer. Try that again. Over here, right? So these links have been reset and the bridge is now complete. So we now have 15 leads to 31, which leads to 40. And in the reverse, 40 leads to 31, who leads to 15. So with the doubly link, we should be a little more careful of order, because if I try to reverse these two, if I say temp next equals a new node, I can't then say temp next previous equals 31, because now temp next previous is this number 1 link here. So we just have to be here. We have to go through the new node. Its next is also 40, and then we can get back to this back pointer. So that's the only little wrinkle you want to be careful about when you've got multiple links that you need to manage. Right, so you'll see in these various branches, we have next and last. Right, next and last in the various branches as extra maintenance, and pretty much the key difference between this insert and the insert we saw in the previous code file. Any questions before I clear the drawing? All right. Let's skim through this. All right. Let's see, we've had 10 minutes of break. We've had about 20 minutes for labs. We have 30 minutes of lab left, and there's a break. Okay, so that means we're roll into lab time now. So let's talk about the labs that we still have here. Array-based stacks and queues. All right, the key thing with this one, right, the front and back wrap around, making this a circular array. Count should be a member. Some of you try and do some math, which doesn't work too well when the front is actually a larger number than the back, because the front can actually be larger than the back because of the wrapping around. So it's just best to have that as a extra member. It's just as an int. Initialize it to 0. You add, you increment, you remove, you decrement. It tracks how many number of data points are actually being used in the array.
I have a question.
Mhm.
You said something about like using the new keyword. Why would we need to like use that in this lab?
For the array-based queue, you wouldn't have to use that in this lab.
Oh, okay.
Not for this lab. Any other questions for the array-based queue?
So I
Array-based,
have a question about mine.
yeah, we'll get to that when we get into the lab section.
Oh, okay.
Array-based stack, this one's easier because the stack just goes up and down, right? Count is synonymous with top, right? So this one's not submitted. It's just an exercise. You can call it count, top, whatever, because as you increase the number of items, the top and the count move in tandem with each other. You've pushed one item, the count's 1. All right, so you push at the count 0, the count goes to 1, and then you're done. This one's pretty straightforward. Binary search, right? Also, just an exercise. Code for this is in the file section if you get stuck on how to code it. Linked list, right? This one's just the basic one. You can take the code that I have in the file section and just strip out the parts you don't need. You can keep the ones that you do, because we just keep adding to the front of the list, right? Just keep adding the head, aka push. And you just need to add a print method that prints from the head until it gets to the end. You can see it just prints it in the reverse order in which the values were added. If the lab is not due or graded, you can just post it in the labs channel in Discord, and we can have an ensuing discussion about ways to make it better, way it's broken, whatever we want to discuss on that one. And that's everything. That's got a date before next time. Wait, no, today is the 31st. Okay, moving along. And the sort, I'm going to change the date in the sort because we haven't talked about sorting yet. Let me go do that right now. Do. Push that. Okay. All right, link-based stack and link-based queue. It's probably easier to do the stack first because stack is a simple data structure, only needs to worry about the one end. Count is an integer, top is a node. So top would be a pointer, right? Because it's link-based. So here you definitely need to use new keyword because these nodes have to be allocated on the heap for them to live beyond the push function's scope. Methods are named push and pop. Push accepts a number, adds it to the top of the stack, and pop returns a number from the top of the stack. If there is something, if not, just print a message saying the stack's empty. All right, so you want a node class and the stack class. Everyone sort with me on this one?
Did you say to use a pointer for top?
Yep, top's a pointer.
Okay.
And whenever you see a node reference, that would be a reference type or a pointer.
Oh, okay.
All right, you can take your stack code and then turn it into a queue code. Add an extra node to track the other side. Count logic pretty much stays the same. Rename your methods from push and pop to NQ and DQ. And just change where it's working. So now NQ, instead of working on the top, would work on the new node representing the other end of the list. And DQ is pretty much the same. Takes it from the front of the list. That front pointer slides down. And that's pretty much all there is for that one. And so, assuming I still have people here on the wait list, I will post these in the labs channel on Discord so you can see the specifications instead of just looking at a recording. If whoever records it posts a link to that. Let's see. That should cover us till next time, right? So we have the first test coming in next time. So you want to make sure you get familiar with the practice test amongst all these other fun things. Discord link again. Yes, the Discord link is right up here in the syllabus, Discord. And I can drop that in the chat here as well. Yeah, well, rest of tonight is break and labs. We can go and work on lab. So ping me your code in Discord, whoever would want to talk about the code, so we can go ahead and I can bring that code up in online DB and we will poke at it and see if it takes the pokes or not.
Are you posting the examples for today somewhere? Where's the Google
Posting
Docs?
the Google Docs. Yeah, they're
Yeah.
all up here in our folder.
Oh, okay.
Right, put the link to that in the chat. It's also on the syllabus page.
Thanks.
Mhm. Okay. To myself. Post lab to Discord.
Are we good to go, Professor?
Yeah, so if you don't have questions, it's all lab time and then break the last 25 minutes of break, we'll toss to the end of class. So rest of tonight is working on labs. So if you got questions on code or your code, send that to me in Discord. And we'll take a look at it. So we're gonna look at this. All right. Let's We got here int star q. Do 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 do. So you got the array here twice. So we don't need it to be dynamic for this lab. So I'm going to eliminate the dynamic part. So we don't need the deconstructor. And we will use that. So here's one of the problems where DQ is being nonlinear. So I'm just going to delete the loop. The moment, get rid of that in a second. Front equals back. It's probably best to test this against count. Recapitalizing syntax. Okay, Pascal. Okay, sorry. Count is 0. The list is empty. Yeah, this one gets a little bit tricky, especially when we have wraparound. I'll come back to this one and take a look at that in a second. Q front, looking at the front element, change this one to count as well. And we will do some tweaking here. All right. Still recording? Yes, we are still recording. Right, count should always be 0 to start. Front, back. And we don't need 2 places, so we'll do that. Max size not actually being used, so we'll strip that out as well. I'm trying to, the intention is not to just slaughter the code, but I'm just trying to strip away all the parts that are beyond our minimum requirements, and then we can start folding in those layers back on top.
Oh, okay. Thank you.
All right, so here's the basic components of the Q class. Right, so these are global functions. Right now you have Q and Q is a global function. And a global function doesn't know anything about the Q class. So you either need to pass along a Q object, which I don't recommend, or we need to move this code into, oh, it's not global object. Sorry, you should get that is this one here. Okay, that's the constructor. I'm going to change these just a little bit because I prefer that style. This we tabbed over. Okay, it's not a global function. That's just tabbed over. Okay. So the count is 0, or rather 10. The queue is full. Otherwise, the back equals the data, and this is where we can make it circular. If right back equals 10, then back is equal to 0. So this makes our NQ circular. Just make sure things lining up. Don't need an extra return statement there. In fact, one of the things we can do, reduce the amount of code, is because this is returned, get rid of the else altogether. Because if we're full, the method leaves. If we're not full, we do our basic add operation. One of the things you can do to make the code shorter is move the plus plus into here. Doesn't much matter. This is what's going to make the NQ part circular. DQ, do the same thing. Count is 0. We are going to cut short. And if it's not 0, we can go ahead and pull from the front, right? So we want to do a couple things. Dequeuing should return back the data. So I want to add the data equal to the array at where the front is. And then we'll do the same thing that we did with the back. We'll increment the back, the front, and then we'll do a test. See if the front is at the max size, and if it is, front wraps around back to the 0, making it circular. And then we return back our data. All right. Okay, so the loop to dump the contents, which is always good to have that sort of seconds from this question. Yeah, if you don't have the labs, you can go ahead and bail. Work on program 1, ask questions about program 1. Okay, so starting at the front is what we want to do. And just call it loop count 0. Well, the loop count is less than count. I plus plus. Spit out the Q, and then here we need I to also behave circularly as well. If I is equal to 10, then I equals 0. So we're going to start at the front, we'll print the front. And if there's 1 item, we'll go 1 past the front. If there's 7 items, we'll go 7 past the front. Just 1 second. Echo, stop. The key thing is our array. All right, where's my annotate? Our 2 middle tiles. All right, so if we have the array, right, the front might be here and the back might be here. We have, right, 2, 4, 6, 8, 10 sort of thing. So we set I to the front, and I keeps incrementing until it resets back to 0 and prints it out, That's what we're going to try to get going on here. You don't need a return. If we're not returning anything from a function, having a return something at the end is just unnecessary because that's the last thing that a body does anyways. Q front. Right. That just basically peak methods. That's good. Let's see what I broke. We do see out not declared in the scope. Okay. Wrong language. All right. Someone help me fix my brain. What am I doing wrong here? Include. Sorry. Thank you. Man, it's stuck in C# mode. All right. Yeah, no semicolon. All right. Turn this one. Q is not declared in the scope. And do Q display. Error request. Request from error is non-class of type Q. All right. Do. Christmas of non-class type Q. Interesting. Do. Now you switch to a compiler who are more familiar with their error messages. Solution. Let's see. Build fail. Do. Totally doesn't like the style syntax. All right, fine. Yeah. Yes, pointer. I don't know what's going on exactly. It's not liking the stack variable, which should more or less be okay. I don't recommend using a stack variable, but we'll see. All right, now it's compiling over here. So we switch back. See if it wants to run in the online version. There we go. I didn't like the stack variable. I don't know why it didn't like the stack variable. Definitely have bugs in my code here, and that's why I'm going to go back to Visual Studio so I can step through the machine, Q display, count is 0, Q is empty, all good there. NQ. Right back, presently at 0. And that. And 20 drops in, back goes up by 1. Don't wrap around. NQ. All right, I'm pretty sure NQ is fine. See, it's one my display method. All
I
right,
think really this one is the Q-based array-based Q.
this is array-based Q.
Array-based Q.
Yeah, what is the array is empty? Why is the array empty? Unable to. Okay, there it goes. Q is definitely being populated fine. Q display. Oh, there it is. All right. I don't know what I was seeing. Oh, I forgot to increment my count. There's my bug. All right, NQ. Plus plus. Let's see. That would be minus minus. DQ. And plus plus. Okay. All right, fun bugs. Yes, I broke the code. I forgot to increment my loop counter, didn't I? Let's increment that. That would be helpful. No. Yep. Let's try that again. All right, 20, 30, 40. A little bit of a white space problem here. So let's fix that. And at the end, a new line is always a good idea. Run through it again. All right. We need more printing. NQ should. Debugging purposes, try to NQ. All right, rather try to DQ. Get my functions. Oh. DQ. No data. So yeah, try to NQ. Data. For my End lines always useful. All right, so in Q 20, 30, 40, 50, dump it out. It's looking good. 60 comes along. Q 20, 30, deleting. Okay, now let's just insert and is full in here. No count is public though. All right. DQ. Q count less than 10. Q and Q count. And might as well do the display while we're at it. And of course, I forgot the original purpose was that bug about it being for everything. So I'm just gonna make sure this is good. I will post it back and then I will get back to your version and make sure that things, let me do a quick comparison. Right, so I have a feeling this won't look right in the original version of the code.
Is there somewhere I can access like the part you just edited? Because I think I'm missing some things.
Yes, I am dragging this back into Discord.
Okay, thank you.
File name is totally wrong. File name is wrong. But it is back. Should be uploaded. Yep, there it is. And let me go back to your class definition along with my main. Go too far. Okay. Okay, so it's not compiling. No default constructor. No default constructor. Okay, I'm going to get rid of. So that's the only change I'm making to your version. And right, so this is your version of code with me trying to run. It's kind of a, when it was good for your test scenarios when it went partly there,
Yeah.
right? But when we tried to get it to the full case,
Uh-huh.
that's when it fell apart.
Oh, okay.
So yeah, so that's what I was trying to comment on. Yeah, so you can check modified version with your version. You want to at least fix the DQ so that that's constant time. But yeah, the problem was there as I suspected. So let's see, dog food.
Okay, thank you so much.
Definitely, let's check out your code. What questions do you have?
Yeah, so I was looking at the int SLL.cpp and I like mine did anything a few things different.
Okay.
Like for the struct, I don't have like a default constructor for my struct. Do I?
You might need it depending on the compiler that you run on. It might be a problem. Windows runtime tends to initialize the 0 just fine, right? So let's see. Test codes all comes out, so uncomment that. Let's see what it does. All right, so 1, 2, 3. So things are looking fine here, but some, like if I try to take the same code, the online pilot, maybe it won't run. I've had people have this issue, so it's good here. So most runtimes, if you do not provide a default constructor or any constructor, a default constructor is provided for you, and it does a mem set on everything. So everything's 0. So ints are zeros, chars are zeros, pointers are 0. Everything's nice and 0. I've had students with different versions of different compilers. Same code that works here in Visual Studio doesn't work in VS Code or Xcode or whatever it is, because the runtime doesn't have that same feature. And the pointers are just some sort of garbage value, just like C style code would be. Like go to C style code and you don't initialize a local variable, right? It has this other weird value that looks like garbage. It's not actually garbage. It's like a bunch of C's and a bunch of zeros for the upper and lower bits.
Okay.
But it's always a good practice to be explicit in your code instead of relying on implicit nature of the language, unless it's just so common that everyone's following that pattern anyway. So you're being consistent with industry convention. Yeah, the code's running just fine. I assume that was the expected output.
Yeah. Would I also need like a destructor for either my struct or class?
In practice, yes. For this class, I don't. You have all the memory leaks you want. I don't care about it. You want it is because we're not using right the garbage collection types, the GC new and all that fun stuff. You're using the regular new keyword. It is your responsibility to delete anything that your code creates once it's no longer needed. So the deconstructor would be there for you so that when if we're only using it in main here, but when this local variable goes out of scope, it should in turn cause the deconstructor to be called, which could then clean up memory. Our applications are so short-lived, the code have to have a significant bug for the memory leak to actually become problematic. And we'll talk more about memory leaks in Windows and having to reboot. Then that's a different story.
Okay, so the only time I need to like write an actual deconstructor in my code is like if I want something to happen on delete. Otherwise, I can just do like delete test or whatever.
Yeah, the deconstructor, the purpose of deconstructor is to enforce cleanup, right? The job, just like so, the constructor's job is to do the memory allocation. It's the deconstructor's job to do the memory deallocation and other potential cleanup, right? You might have like a database connection open or a socket open or other external resources that object is got a handle to or a file. So that's where that logic belongs in C++, is in the deconstructor.
Okay, but I just want to confirm that I don't need like the tilde thing to delete. I don't need to write one of those. Like if all I want to do is just do like delete this object, that's all I need to do, right?
Yeah, you can put yeah, you don't for this class you don't need a deconstructor. It's just something you want to do when you're writing production level C++ code.
Okay. And also for a lot of these like labs we're doing, I just saw in like the CPP files or whatever, whenever I'm making like a new object from a class or a struct, I've been doing like the class name, the asterisk to make it a pointer, and then I do like
Yeah,
name of
67.
that. Yeah. Would I be able to do that with just doing like list q no asterisk test equals new list q, and then I do test dot in q and all that?
Yeah, so if you're doing it without, right, then stack var dot nq 5 and stack var display. Right, and see, there it is. It just means this is a stack allocated variable. And since there's the one, it's the one off, you're not adding these queues into another larger construct, it's fine. Since it's a stack allocated variable, parameter passing these things, then it gets a little bit stickier because of the way it was allocated and it's copying everything, and things can get real unintentional very quickly that way. And a lot of languages don't even support reference type variables being created as a stack allocated variable like that. So it's a pattern to not get used to, because it's a pattern you're going to lose when you go to most other object-oriented languages.
Okay,
Or,
so
of course, the other languages, they're actually what they get rid of this one and they say that this is a reference variable. So it's kind of goes both ways on which way to view getting rid of that.
So to be safe, the doing like the asterisk or pointer way is just like a
Yeah, it's a C++ thing or Objective-C thing. I think Objective-C still uses stars.
I'll probably be doing that more than just like the what was it, stack allocated
Right.
way. I'll
Yeah,
be doing that's heap allocation,
Yeah,
right?
yeah. So this syntax is in line with most object-oriented language memory usage, right? But most other languages, yeah, they simplified things. They just say it, do it like this. C++ doesn't like this because this is a reference type, and that's not a reference, not a pointer, so it should complain, right? Ah, interesting. Standard library, whatever. Yeah, but that's just a language thing. Doesn't matter.
Other languages though, they have like automatic what is it, garbage cleanup or
Yes, Java and .NET runtimes have built-in garbage collection. C++ has that option now if you want to rewrite your code base to using GC new. There's GC new. Actually, it has to be a completely different syntax and all kinds of fun stuff. And the syntax is even different. Don't quote me on any of this stuff because this is not what I'm familiar with, but GC stands for garbage collection. And
is
that
there
is
like
way beyond the scope of this class. So
Yeah,
we,
okay.
we will talk about what a garbage collector is towards the end of the semester.
Okay, got it. Do you see any like major flaws with my code or anything like that? Or
Yeah, it's always a good idea to have a constructor, but this is a struct. So actually this is fine. Struct.
okay.
Structs usually don't, yeah, you wouldn't have a constructor. So I didn't notice that before, but otherwise, some people prefer being explicit, saying that's the private section, which is the default, whatever.
Mhm.
That's totally convention, doesn't matter. Null is partially supported. Not all compilers support null, so you might have to say 0 instead of null. Just want to be careful with that. Back and front equals null. That's a little bit interesting. Back and front is equal to null. Okay. Is you're adding two memory addresses here, which is going to give you a weird memory address. But unless they're both null, that's going to be null. It seems like an unnecessary operation. This could probably just be simplified. So looking at one of them, because if the back is null, then the front should also be null.
Okay.
But I'm not gonna, that other way seems like it has the potential of catching a bug where someone set the back to null, but actually forgot to set the front to null, and this will actually return null because null and anything is going to be null.
I mean, I'm also keeping a count. I could do count equals 0 because this is just for inserting the first node here.
Yeah. From a readability standpoint, right? What's more readable? If right count is equal to 0, meaning empty, or this meaning empty. Right? Because logically it's the same line of code. The question is which one gives you, which one's easier to understand that the list is empty.
Okay. Yeah.
Right. Otherwise it doesn't much matter.
Wait, so I have also like null values there. Should I change the null values to zeros?
It doesn't matter to me. You can leave it alone. This compiler is handling it fine. So I would just leave it alone, but I don't know if they move that into standard library in C++. I'm used to C for null, so I forget which standardlib.h, so I don't know. And C++. Null is probably preferred. Let me see if Visual Studio will tell me if that's still, is that still a macro in C++? It is macro. Yeah, so see, it is just 0, so it's synonymous, just a macro.
Okay.
Or or void star 0, which void star point not type of pointer 0, so it's effectively just 0. Either way, just null is preferred where it can be used. Because comparing against 0 seems a little bit weird unless we're comparing integers. Display, white space, and line. Yep. Yeah, the code looks fine.
Cool. Thank you.
I have a question.
Yep.
Can we check my code?
Sure. Yes, Vincent. Commas for the linguist lab. No, you can assume user input is well formed, and in the exact way that you expect the user to give you the input. If the queue has to be a circular array, why does it say, right? So a queue is full when our count is 10. Right? The queue is not full when the back gets to 10. Because the back representing a location in the array and where the front is not an indicator of the array being full or not. It's the count being full. Because if we have 10 spots, I can hold on to 10 values. In the beginning and the front, just circle around. And the reason we're doing it circular is so we can enforce our abstract data type rules of constant time adding data and constant time removing data. So it doesn't matter how full the queue is or how massive the array is. It's going to take the same amount of time to add and the same amount of time to remove in all possible states that that data set is in. Okay. Drop your code into Discord and I can bring your code up.
I dropped my code to the Discord.
Mm-hmm. Yeah, we've been doing it in the labs channel, so that works.
Okay, so just give me a second.
What's your question, Kristen? Or are you Kristen?
Yes, my name's Kristen. I'll drop my code in the Slack channel for review. Let me see if I can pull it up here. One moment.
Okay.
It's for the array-based queue that's in question. So let me go ahead and upload. And to be honest, I'm having a hard time following in class, but I try to do a skeleton based off of the file that you have. And so what I tried to do was repeat the NQ to count for the max size of 10 and expand it so it outputs 10 times. But when we look at my output, it doesn't allow me to write out the final NQ to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the entire list. And then it does a DQ at the end.
Okay, so yeah, so everything looks fine except for the print. Right, so the print, because back and front can wrap around each other. It's like I had in the drawing earlier. Let's draw it again. Right, our very crudely drawn array here. The right, normally, right, the front and the back. Right, the front and the back have this relationship where the back is always greater than the front. But it stops being true as soon as the back rolls around, because the front can move up to here and then the back can be over here, which means the front is set to, let's say that's 4 and the back is 0, right? 4 is not less than 0. So this loop doesn't loop. So what we want to do is switch that loop to work on the count. Right, so int loop count. Then we can do this is equal to the count while loop count. What did you call it? Node count. And we do int index equals front. Right. So spit the index out. We will decrement the loop count. We will increment the index, and we will wrap index module equals. I think I saw max size. All right, so I just need to get to errors hit. There it is, max size from 2 to 10, front, back, node counts 10. And let me look at your test code. All right, while in queue, till returns false. All right, and then we stop printing. Fine, and we can call the print. Let's. Do we have any DQs? Let's do a couple of DQs before we get to here. And spit that out. Fold that out.
Is there a particular reason why we have to DQ 184?
Oh, because I didn't see that you already had a DQ on 181. So nope, I don't need an extra one. I'm just pulling out an extra one and then added a print. See that print's looking good. Okay, so right, so we have your queue up to 10. All right, so we started at 1 to 10. We DQ'd 1, pulled the 2 out, then we added 2 100s with filling up the queue, and then we spit it out. Right, which means these actual values are in the beginning of the array. So we can add another print method that does a dump for the full contents. All right, for loop. Max size, so we can see the true state. And let's add the dump to the end. Run that again. Right, see, we can see this is the actual array state where the last 2 added values are in the first 2 positions as they should be because it's a circular array. And it's printing out in the proper order because 3 is the oldest value. So when we do our regular print, it prints out the oldest value to the newest value, where the front's here and the back is here or there, depending on precise code implementation, but the front and back are in the middle of the array, and the queue is still handling things in the proper order. So if I were to do a DQ now, it should pull out 3 as the oldest value. Was I still running? Let's try that again. What's going on with my clean build? Visual Studio just likes to do this sometimes. freak out. Just make sure that that's eventually stopping. Okay. Hold that DQ. Okay, good. I must have just had a window. There we go. Still open. All right, pulled 3 out. As we should, because 3 has been in here the longest. Yeah, so other than this print function changing, so I just posted in Discord that everything's fine.
Okay, thank you.
Mhm.
For the dump, we have to add that as an extra function because,
I just added it to easily show what's inside the array.
okay,
Yeah, I mean, and it's just a basic for loop from 0 to max size, spinning it all out. And we can see the difference between the queue state, right, where things are in the queue versus the underlying data storage. Right, so dump is giving us the underlying data storage and just its raw, unformatted set 0 through 9 indices, whereas the print is giving us in the proper queue order of who would be next and who's coming up, who's in line after them. So it shows you the whole line from front to back. Okay. So what's Nafas? What's your question on this one? Yeah. Let me. Sorry, one. You can definitely just print error statements. I'm not expecting try catch in our code here. It's definitely things that would be a good idea, but I don't need that in your code. If you want to use it, I'm not going to stop you from using try catch. Try catch is absolutely things that are the way, common way to handle errors. Okay. Go ahead. What do we want to talk about with this code here?
So you commented that the order is not right or something like that, and I don't understand like
All right.
what did I do exactly?
Okay, let me check. All right, let me change this code to a loop so the numbers are I equals 0, I less than 8, I plus plus r dot qi, and then we got a bunch of DQs. Cut a few of those out. In fact, let's put that into a loop. And I equals 0, I less than 3, I plus plus. Since that's copy paste code and copy paste code is easily replaced, then let's NQ some more, let's DQ some more. We'll see how well it strains. In fact, let me change my numbers. Okay, it's NQ 8 through 15. Try that again. All right. Queues full. Wait, what are we printing here? Or we're playing display queue. All right, let's. Oh, these are dequeuing. Okay, let me. DQ. Oh, DQ is not returning data. Oh, that's a problem. Let's fix this. What is DQ doing? DQ is not DQing. All right, so that's a problem. It should be sending data back. So data was our front. And return data. Okay. Check failed. Yeah, it didn't initialize. Let's see. Q is full. Max is 10 here, right? 10, right? So you can see here. Let me make sure I did this in order. Let me display. I think I've got. All right. Queuing 3. See out and queue more. And this doesn't need to be a loop. Just paying close enough attention to what I was changing. And let's see what's in the queue, right? So queue should be full at that point. So we should see 10 values in the queue if Visual Studio wants to work with me. All right, so we're in queuing more. All right, so we built the queue. I didn't print it out. I should print it out. Let's print it out. Let's display the queue. All right, we added 8 items. All right, that's looking good. We pulled out dequeuing. What is dequeuing? 3 items, right? Okay, dequeuing 3 items, dequeue 3 items, enqueuing more. And it's full, and then we print it out. But I have 1, 2, 3, 4, 5, 6, 7 items, and the queue is full. How could it be full if I just dequeued 3 items? All right, so this was the bug that I'm referring to, because the queue isn't actually full. It has room for 3. So let's take a look at the code. Right, front back count, constructor, you're doing negative 1 style. All right. Displays getters, all right, is empty. And okay, NQ, back, NQ, front. Yeah, so NQ shouldn't care about the front at all. NQ should only care about the back. So having front logic here and in the NQ is a little bit weird, but here's, you're not wrapping around. So this is not circular. So the array is not being circular. So it basically, after you've added 10 things to the queue, you can never add any more, even though you've taken everything out. So we can completely, right, dequeue everything. We could dequeue it all. Right. Let's go 13 times, whatever. All right, queue's empty, try to enqueue some more. Yeah, now it works. If you go all full empty, then yeah, that's right, you have some reset logic. Then it gets back. So I guess it's when we stop just short. And we need more white space there. The queue gets just before And we still have items on there. And trying to NQ more, it's like, no, can't do it. All right, so that's the part you want to tweak. Right, this is module equal max size. This will wrap it around to 0. When it gets to 10, you want DQ to do the same thing on the front. And resets around. So this front equals back logic, and then all of a sudden going back to -1. This is specifically the bug I was talking about, causing it to get into an invalid state.
So, but isn't it that if the front equals back and they are both at -1, which means that the queue is empty?
Yeah, best way to look at if the queue is empty or not is count. Right. So what does this empty look at? Yeah, how would you look at the count? Turn count equals 0. If count is 0, it is empty. Yeah, and that's the thing. This is the other reason why I don't favor using -1 for variables that track an index, because -1 is not a valid index inside the bounds of the array. Since it's not a valid index in the bounds of the array, it's out of bounds if you were to try to access it. And of course, C++ be like, whatever, because it tends to be a little bit helpful or too helpful in that regard. And the very first time you NQ, you set it to 0 anyways. And then the back goes from, are you ever setting back to equal to 0? Right, back is -1. You increment it to 0. So the very first time you come in here, back goes to 0. Then you set the 0 to the value, then count goes up. And then your pre-increment, which is fine, which is what you have to do if you're doing -1. Like my samples, I start at 0, and then I drop it at 0, and then I go up 1. Yeah, I find trying to use front as a measure against back, because of the circular nature, just increases the code complexity. Count, which is part of the reason why I have it in the lab specification, can do the same job, and it can do it in a much simpler fashion. Either we are at capacity because we have count items equal to the max size, or we are empty because count is 0, or we're in between where there's some space available. Yeah, we know the queue is wrapping when it hits either the max size or where it's trying to go beyond the max size. Right? In this approach here, this one's going, if it goes beyond, if it goes to 10, 10 modulo 10 is 0. Right, so 9 modulo 10 is 9, so that means you're in the boundaries. When back goes to 10, 10 modulo 10 is 0, and we set back to 0. And this is also in the wrong code name file because I've been reusing the same code file. Still the wrong file name. But some of my updates are in Slack. You can be saying Slack, Discord, in the labs channel.
But I didn't get that. So when we do in queue, so I said that if the queue is full, if the queue is not full, then we are going to check that if the front it's -1 or not. If the front is -1, I bring the front to 0, which is the index of the first
Right.
index of the array.
And NQ
And
shouldn't be touching front,
why is that?
because NQing happens at the back. Right, so I'm making
Okay.
additional tweaks. DQ should care about the front, right? Shouldn't care about this. So I'll make additional code tweaks. That's an extra else. Ooh, grabby there. Okay, so data equals front. So you have to move this up to be match your -1 pattern that you have here. So front starts at -1. We increment it to 0. We pull the first element, decrement, and then wrap it around. And display, I'm going to just change this to, because this is broken, 0 less than. Well, I'll leave it alone for now. It's only broken once we start wrapping. All right, Q created. I've got the fun garbage value. Let's see what I do with my timing there. I equals front. Yeah, because car particles front was -1 to start. Front, -1. All right, like I was talking about earlier, invalid boundaries. It's fine. We know why it's printing out garbage the first time we run it. All right, create the queue. And because front started at -1, slightly out of bounds with my code changes. NQ more, count is 8. And you can see the additional display codes aren't working because they're starting at a large number and they're not wrapping around. So that's why we want to make the same code change as we did with the earlier lab, because the front is going towards 10. And there's going to be a point in time where the front is 8 and the back is 2. 8 is not less than 2, so we call the display Q. All right, we can add a little C out here. Q. See our empty semicolon. Yeah, inline. We don't need quotes for inline. Right, so the queue is showing empty, even though I just NQ'd a whole bunch of data. A whole bunch of data was NQ'd here. And the queue print is failing count. That might be correct. That's probably correct because count's going up and down independently. So there are 8 items in the queue, but nothing's printing out. So we need, right, so it's better to use the count. Use count to control the indexing. Or not the indexing, the number of looping of loops. Right, and we already made this code change to the first code sample that's in the labs channel. So we already have that coded, so I don't want to code that again because we'll pass in the class. But I will upload.
So this code is not working though. It's not the correct one.
Right, it's mostly correct. I mean, NQ is constant time. That's important. DQ is constant time. That's important. And it is now circular. These 2 lines of code make it circular. Count is incrementing properly. Count's decrementing properly. Do I even have a display requirement in the lab? As long as it's NQing and DQing correctly. Yeah, see that print method that's broken isn't in the requirements. Thus, it doesn't count against you. That it is broken. And we've fixed the other parts. The code changes as is sufficient enough to get full credit.
But how can I fix the displays?
Yeah, look at the other code file that I uploaded earlier in response to the first one we did.
In the Discord?
Yeah, it's in Discord in labs because we fixed the same issue already in the other one.
Okay, thank you.
All right, well, talk to you all on Discord and see you next week.
Thank you. Bye.
Yeah.